Welcome back. So the last time we were proving some properties about derivatives. We proved the quotient, product rule, etc. We were in the process of proving something that we would have thought was trivial. That is, if the gradient of f is identically 0 on a connected open set, then f is constant. Now connected open is the same as path connected and open. But it is more convenient for us to use connectedness rather than path connectedness. Again, what does connected and open mean? It means that you cannot write this open set as a union of two sets A and B which are disjoint and both open. That is, you can't write it as a union of two blobs, both of which are open, right? So let's see how to do this. So just a little point here. So suppose you have a connected set, connected open set for that matter. Suppose you have a connected set S. If you take any subset of it which is not empty, okay, and which is open and closed. Okay, what does it mean to be closed and open? So suppose you have a set S, right, and you have a subset, let's call it A. Okay, A is not empty. A is a subset of S. A is open in S, which means A equals S intersect with an open set in Rn, and A is closed in S, which means the complement of A in S, which means the set of all things in S which are not in A, that set is also an intersection of S with an open set of in Rn. Okay. Such a beast, such a subset A must be all of S itself. This is the point that we will use. A non-empty subset of a connected set which is both open and closed in the set is the entire set itself. Why is it the entire set itself? Suppose it's not. Suppose it misses something. The thing that it misses will be open in its own right, right? So if it misses something and that is open in its own right, why? Because this set is supposedly closed by assumption. So in other words, your set S is a disjoint union of two open sets, and therefore it is not connected, which is a contradiction. Okay, so this is what we will use. Okay. So consider, so fix A in U and let S all x in U such that f of x equals f of A. So S is not empty. Why not? Because A is an S. S is closed. Okay. So why is it closed? I claim this follows from the continuity of f. Okay. Why does it follow? This requires a small argument. What does it mean for S to be closed firstly? It means that the complement is open in U, meaning what? What does the complement consist of? Consists of all x so that f of x is not equal to f of A. So if you take a point in the complement, if f of x is not equal to f of A, then for all x in a neighborhood of that x, f will continue not to be equal to f of A. That's where continuity is used, and I'd like you to think about it. Okay. So please think about why this is the case. Pause the video and think about it. What we shall prove is that S is open. If we accomplish this, then these three properties together with connectedness imply that S is all of U. Once again, why not? Why is that the case? Suppose S is not all of U. Suppose S misses something. In other words, the complement of S in U is not empty. Then the complement of S is open because S is closed. So U is a union of two sets, S and the complement of S. These are both open in U and they're disjoint, which means U is not connected, and that's a contradiction. Okay? So all we have to do is to prove this, and then we will be done. There are other ways to do this, play the same game, but this is the cleanest, and it illustrates a useful way to use the hypothesis of continuity. Okay? Right. So consider an open ball around some point that is contained in U. Okay. U is an open set. After all, there is some open ball which is completely contained in U. Take any such open ball, claim B is a subset of S, and hence S is open. So proof of this claim. So first of all, if you take B plus T times X minus B, suppose X is in B, of course B is already in B. This is completely contained in B for all T. In other words, this line is completely contained in the ball. Yeah? So consider the function g. So this function g is a composition of two continuous functions. This is a continuous function. This is a continuous function, right? So this function g is continuous in its own right. G is differentiable on 0, 1, and the derivative of g is 0. Indeed, if we look at the definition, what is this? This is simply, by definition, the directional derivative at this point, which is this is 0. Why is it 0? Because we've assumed the gradient is 0, which means what? The derivative is 0. So it's continuous on a closed interval, differentiable on an open interval, the derivative is 0. So by Lagrange's mean value theorem, g of 1 equals g of 0, which means what? If g of 1 equals g of 0, what have we concluded? That means g of x 1 is f of x equals g of 0, which is f of b, which is equal to f of a by assumption. In other words, b is completely contained in S. So we are done. Okay. So notice that this theorem might appear to be trivial, but it's not as trivial as it looks because of the hypothesis of connectedness. You need to use that hypothesis somehow, right? Okay, so this is the last property for now. If f is a linear map, in fact, for linear maps, you don't even need this. If f is a linear map, then f is differentiable everywhere, and happily enough, the derivative is very simple. The derivative acting on h is basically f acting on h itself. Okay, how do you prove this? It's very easy. F of a plus h minus f of a minus f of h is basically 0 for all h, and therefore goes to 0 as h goes to 0, which means this is the derivative by definition. This is the analog of saying if y equals mx, dy dx is m. So in other words, dy dx times h is mh, which is basically this function acting on h. Okay? So in that sense, the derivative of a linear map is itself in that sense. Okay? In one variable calculus, that would have been a very odd statement to make, because the derivative of a linear function is a constant. But when I talk about derivatives in more than one variable, I mean I'm treating them as a linear map. So this is the correct thing. Okay? Right. So now we have enough weapons in our arsenal to conclude the differentiability or the lack thereof of several functions, and to be able to calculate them as well. Let me give you a concrete example of differentiability. So consider this function f from n by n matrices. N by n matrices are basically Rn square. Basically, if you simply arrange the entries of the matrix as a huge vector, then you just get Rn square. Okay? So n by n matrices, which is Rn square, right, given by f of a being a square. So the question is f differentiable? If so, what is the derivative at a point acting on h, where h is in Rn square, which is also the same as m matrices? So the answer to this question can be given in two ways. One is, so first of all, why is f differentiable? The components of f, the vector valued function f of a, are as follows. F of a ij is aik akj sum over k, right? So in other words, these components are polynomials in the entries of A, and polynomials, and hence C1 therefore differentiable. Okay, so the fact that f of a is differentiable is rather easy. The question is, how do you actually calculate the derivative? Now there are two ways to do it. Okay, one is two ways to compute, to calculate df of this. One is just by brute force. What is df(ah)? It's simply obtained by taking the partial derivatives, remember, namely df(ah) the ijth entry is simply you take the ijth column, this particular entry of f, and you take the partial derivative with the klth entry of A and hkl sum over k comma l. I hope this is clear. How do you compute the derivative matrix of a vector valued function? You simply, if you want the derivative matrix, so rather not the derivative matrix acting on a vector, right? How does one compute that? So the calculation, the ijth or the ith, so these are matrix valued functions, but in general the ith component is simply obtained by this prescription, so to say, right? I mean, let's recall, suppose you have, let's call it g. G is, say, a vector valued function. If you take dg, this is a matrix acting on a vector h, is what, right? This is simply the ijth entry would be dg. I mean, maybe if I write it as gradient of g1, gradient of g2, etc., h1, h2, so on. So if you want, let's say, so this is a column vector. So what is the ith entry of this column vector? It's obtained by multiplying row with column, right? So in other words, this is simply dgi dxj hj sum over j. Except here, so you have two indices, so it is dfij with respect to, instead of xj, it's xakl, hkl, right? So now that we know this thing, we can now do it explicitly. So what is fij? It is sum over, let's say, m a I m a m j. So df dakl times hkl is what? Kl and m of the derivative times hkl. Okay. What is this equal to? Right. So you can of course use the product rule, so to say. I am doing this in its full gory detail, so that because this is the first time we are seeing such a complicated example. At this juncture, it's actually very helpful to use a symbol. What is this derivative? This derivative is 1 if these variables are the same, if I equals k, L equals m, and 0 otherwise. Likewise, this derivative is 1 if k equals m, L equals j, and 0 otherwise. So in other words, the only terms that will survive in this summation, if you will, let's only keep k and L, this summation, are ones where m equals L for the first term, right, and k equals I here, right. So in other words, there is no summation over k here. Maybe it's much more efficient to write them as two separate things. So the first term is the summation over L. You're not summing over K because the only term that survives is when I equals K, right? And L equals M. Sorry, HIL plus. What about this one? The only term that survives is when L is J and K is M, right? So in other words, it's L is J and K equals M. Okay. Now we recognize what these are. What is this? This is simply the ijth entry of the matrix A times H. What is this? This is the ijth entry of the matrix H times A, right? So in other words, very simply, the derivative of f is simply HA plus AH. By the way, this is sometimes written like this. This is called the anti-commutator of H and A, but it's simply AH plus HA. Very simple matrix expression obtained from a rather painful calculation. So sometimes, as we shall see, this is the second way to solve the problem. Using the definition actually makes things easier. Okay, you might think that it will make things more difficult. Surprisingly enough, it makes things easier. What is this? This is A plus H square minus A square, which is A plus H minus A square, which is A times A times H times A plus H times H. Okay. So in other words, this is the so-called skew anti-commutator plus A square, this expression. So A plus H minus f of A minus this is a linear map in H divided by norm H, if you wish, is norm H square by norm H. For matrix norms, like for instance the Frobenius norm, you get this. This goes to 0 as H goes to 0. In other words, this is precisely the derivative by definition. In other words, this is the Frobenius norm. Okay, and so on. So just using the definition can sometimes make the task of calculating the derivative easier, because you just have to identify the first order terms. The second order terms don't contribute to the derivative. Okay, right. So let's move on. Here is another example. So the question here is, prove that the determinant function, which takes matrices, square matrices, and produces a number, right? The determinant of A is differentiable, and calculate its derivative. Right, so how does one solve this problem? Again, the determinant is a polynomial in the entries of A. If you write down the determinant, well, how do you compute the determinant, right? You can compute it row by column, for example. You close the first row and you expand it out in terms of lower determinant. So you take A11 times this determinant minus A12 times this determinant, and so on, right? And each further smaller determinant can be computed this way, right? So In fact, it's what degree of a polynomial it is. Please think about it, right? Why is this a polynomial? That's all I'm trying to justify. I claim this can be done inductively, and the proof is basically what I said, but you please try to do this rigorously on your own. Okay? So as a consequence, C1 and therefore differentiable. Okay, so the fact that the determinant is differentiable is very easy given what we have done so far. The question is, what is its derivative? Let's compute the directional derivative at the identity matrix. The claim is this is equal to H. How does one do this, right? There are a number of ways to do it. What is this after all? This is determinant of I plus th minus determinant of I divided by t as t goes to 0. Determinant of I is of course 1. So this is determinant of 1 plus th11, th12, th21, 1 plus th22, etc. divided by t. Now we can use the properties of the determinants. If we fix this, then these rows add up. This is fixed plus th11, th21, etc. and this is fixed divided by t and divided by t. Okay. Now these t's will pull out, they'll get cancelled with this t. As t goes to 0, this will go to what? It will go to 0, 0, 0, 1, 0, 0, so on. This will be just the identity matrix. So this determinant is simply H11. Okay. Now likewise, you can play the same game here, and you will conclude if you do this thing and you keep expanding it. So as t goes to 0, you can show that this is H11 plus H22 plus so on until Hnn. This is the so-called trace of the matrix H. Okay. So the derivative of the determinant, the directional derivative at the identity matrix, is the trace of a matrix. What happens if the matrix is not identity here? If it is not identity, how can you handle it? I'll leave that to you as an exercise. The idea is to bring it out by using its inverse. So if you have a non-identity but invertible matrix, you can pull it out and use its inverse to compute the derivative. What if it is not invertible? It's a bit more complicated. Since this is just an example, we won't really bother dealing with it. We will only deal with the directional derivative with the identity, just to prove a point as to how to compute it. Here is another fun way to do it, a more elegant way if you wish. If you take a look at this determinant, this is simply the product of its eigenvalues. The determinant of a matrix is the product of its eigenvalues, and indeed these are the eigenvalues of H, right? So if you want to compute the d by dt of it at t equals 0, using the product rule, and the trace is the sum of eigenvalues. The only thing is, this requires a little bit of justification. What justification? The point is, these eigenvalues are complex numbers. So this requires a tad bit of justification to do it correctly. So we won't bother with it, but it's a nice way to do this. All right, we are done for now. Thank you for joining. Let's continue the next time.